Assalamualaikum sir and everyone. My name is Muhammad Mazikri and this is my group partner Muhammad Firdaus bin Hussein. So today we will be presenting our AI project. So for our AI project, we use TensorFlow's image data generator to load and pre-process images for a machine learning model. Specifically, we are working with a dataset of sunflower images and dividing it into training, validation, and testing sets. First, we import the necessary libraries. We use OS for file path handling, image data generator from TensorFlow for image loading and preprocessing and matplotlib for visualizing the images. Next, we define the base directory which contains subfolders for each sunflower subspecies. We point the base_dir to the folder sunflower where the images are stored. We specify a few important parameters like the target image, size for resizing, and the batch size for loading the images. We then create an image data generator instance for data preprocessing. We normalize the pixel values by dividing by 255 to scale them to the range 0 and 1. We also set a validation speed of 30%, meaning 30% of the data will be used for validation and testing. Now, we create the training data generator using the flow_from_directory method. This method loads the image from the directory, resize them, and organize them into batches. Similarly, we create a validation generator that loads the validation subset of the data. This will be used for model evaluation during training. Optionally, we can also create a test generator if we need to evaluate the model after training. After setting up the generator, we print out the number of training and validation samples to get an idea of the dataset size. Lastly, we display a few images from the training set using matplotlib. This helps us visually confirm that the images are correctly loaded and that the labels are properly assigned. So as we can see, the AI found 7,027 images belonging to 3 classes. They also found 3,010 images belonging to three classes, found 10,037 images belonging to 3 classes. So the total training samples is 7,027 and the total of validation sample is 3,010. So next, we build, compile, and train a convolutional neural network CNN using transfer learning with MobileNet V2 to classify sunflower images into 3 categories. The process involves optimization such as learning rate scheduling, early stopping, and model checkpointing. We begin by importing the necessary libraries, including thrust layers, MobileNet V2, optimization tools, and callbacks. MobileNet V2 pre-trained on the image dataset is used as the base model. By setting include_top equal false, we exclude its classification layers, using it only for feature extraction. The base model layers are frozen to retain their pre-trained weight during training. On top of this base, we build a custom model by adding a global average pooling to the layer to reduce feature map dimensionality, followed by a dense layer with 128 units. To prevent overfitting, we use dropout, and the final layer is a softmax output with 3 classes. An exponential decay schedule is implemented for the learning rate, starting at 0.001 and decreasing by a factor of 0.9 every 10,000 steps, allowing for smoother convergence. The model is compiled with the Adam optimizer using this learning rate schedule. To optimize training further, we include early stopping to halt training if validation loss does not improve for 5 consecutive epochs, and model checkpoint to save the model with the best validation performance. Training is performed for up to 20 epochs, but it may stop earlier if early stopping is triggered. Once training is complete, the model is saved to disk for future use, enabling predictions on new sunflower images or further refinement of the model. In summary, this approach leverages MobileNet V2 for feature extraction, adds custom classification layers, and employs training optimization to build an efficient sunflower classification model. Next, I will pass it to my partner, Muhammad Firdaus.
So next, to evaluate the model performance, we begin by visualizing the training and validation, accuracy, and loss over epochs to detect any overfitting or underfitting. Next, we assess the model on the test set using the evaluate function, which provides both loss and accuracy. and print the test accuracy as a percentage. We then generate a prediction for the test set using the np.argmax function to select the class with the highest probability. We fetch the true labels and class name from the test generator. Next, we display a confusion matrix to see how well the prediction match the true label, followed by a classification report that includes precision, recall, and phi score for each class. For multi-class classification, we compute the precision recall curve for each class and calculate the mean average precision, which average the precision value score across all classes. In conclusion, this metric accuracy, loss, confusion matrix, classification report, and MAP help us evaluate the model performance and its ability to generalize the new data. So for the model evaluation, first let's the left graph, the training accuracy, which is the blue line, shows improvement over time, indicating better performance on training data. While the validation accuracy, the orange line, should ideally follow the training accuracy. However, it flattened or decreased at some point, suggesting potential overfitting. So for the right graph, which is the loss graph, the training loss, the blue line, represent model error on the training data, ideally decreasing over time. The validation loss, orange line, start decreasing but later increase, indicating worsening performance on unseen data, potentially due to overfitting. Next, we evaluate the model performance on the test using the evaluate function, which gives loss and accuracy. We also generate prediction and evaluate the confusion metric, which show how. So for the confusion matrix, for each flower type, it shows correct prediction, the dark blue one, and misclassification. For example, Helianthus anus correctly predicted 3,169 times, but confused with Maximilian sunflower 108 times and swarm flower 55 times. The Maximilian sunflower correctly predicted 2,514 times, but confused with Helianthus anus 313 times and swarm sunflower 514 times. While for swarm sunflower, it correctly predicted 2,928 times, but misclassified 402 as Maximilian sunflower. So for precision is a measure accuracy of prediction. High precision means fewer false positive. For recall, it indicates how well the model identifies true positive. And for F1 score, combine the precision, recall, and providing a balanced measure. The support shows the number of examples for per class. Finally, the model achieved an overall accuracy of 86%, meaning it correctly classified the flower type 86% of the time. This metric helps us understand the model's strength and areas for improvement. So next, to further assess the model performance, we can take a random sample of image from the validation set and visualize both the true label and the model predicted label. This will give us an intuitive understanding of how well the model is making prediction on a real example. First, we fetch a batch of validation image using the next function. Then randomly select a few examples from this batch for visualization. We specify the number of samples to display. In this case, we use 5 samples. And next, we select the image and the corresponding true label for the randomly selected indices. We also make a prediction for this image using the model. Now we plot the selected image in a row. For each image, we show both the true label and the predicted label. This allows us to visually compare the model's prediction with the actual label. We also remove the axis label for a cleaner view of the image. By displaying a random sample of image from the validation set along with their true and predicted label, we can visually assess the model performance. This helps us understand how well the model is generalizing and identify different classes. It's a useful way to ensure the model is performing as expected in a real-world scenario. Next, I will pass to Amma.
Okay, so to summarize our MobileNet V2 model, our MobileNet V2 model achieved strong performance with an 85.79% test accuracy which is a reasonable training time for 3,194.56 seconds and a MAP of 0.67. This shows that the model is robust in making predictions across multiple classes, and transfer learning has enabled us to efficiently use a pre-trained model to solve this classification problem effectively. So that is all from us. Thank you.